Hey everyone, so I'm going to do lesson 72 for you because I'm not here today. You could also reference this video on my YouTube channel if you want to rewatch it. Alright, so this lesson is about modeling with exponential functions. So basically you're going to use the properties of logs and exponent to produce equivalent forms of exponential and log expressions. The do now is asking you to create a linear or exponential function. So the first question says, the following table contains additional U.S. Census population data. Use your calculator to create a scatter plot. And they ask you, would it be appropriate to model this data with a linear or an exponential function? Explain your reasoning. So the first thing I want you guys to do right now is take your calculators out, turn them on, and you're going to go to Stat, Edit, and you're going to enter this data in. But remember, with years, you need to make sure you type in 1990 as year 0, and we're going to count up by 10. So 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and 110. This here is your list 1, and then this here is your list 2. Okay, so what you should be doing right now is taking your calculator out, going to Stat Edit, entering in the data. Once you do that, I want you to go to second y equals, make sure your scatter plot is on, and then press zoom 9 to get your picture of your scatter plot. So pause the video right now, try to get your scatter plot on your piece of paper, create a sketch, and ask each other questions if you need help. So now you should see some kind of scatter plot on your paper. My scatter plot looks about this shape. It has 10 dots. It's about looking like that. And the question is asking you, what would be more appropriate? A linear or an exponential function? You should notice that if I put a line through it or a curve, it's more appropriate for an exponential function. So the answer would be exponential. And the reason why is just because it has the shape of an exponential function. The next thing it says is use your calculator's regression capability to find function f that models the U.S. Census Bureau's data from 1900 to 2010. What you're going to do right now is you're going to go to your calculator, you're going to press Stat, you're going to press Calc, and then you're going to choose the function rule that has exponential reg, because we just decided that it's an exponential regression. Press enter, 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 and you will get a bunch of values, and let's round each value to the nearest thousandth. So I'm going to fill in AB to the x from my calculator. Also, this is exponential reg, that's what you should have chosen. Okay, so my A value when you do that is 81.146 by rounding, and 1.013 to the x. Pause the video right now, make sure everyone got that answer. If everyone has, replay it, and we'll continue. So the first example of the lesson talks about a graph of the population of New York City. And you could show that they're talking about rapid growth of population. Rapid growth is similar to an idea of an exponential function. So that's why they're classifying this as rapid growth. So Finn averaged the 10-year growth rates and wrote the function right here. 33,131, 1.44 to the 1t. He used a 10-year growth. That is why he's dividing by 10. So he decided to break up his function into 10 years. Now, Gwen decided to create a regression feature, and she made this formula here, where t is the time in years. So she doesn't divide it into a 10-year growth period, she just goes by years. What they want you to do for the first part is they want you to rewrite the function to determine the annual growth rate for Finn's and Gwen's model. So let's just start with Finn's. Now the only issue with Finn's model is that he decided to raise the exponent to t over 10, meaning that he divided his years into 10 segments. The easier part about Gwen's model is that she didn't do that. she has it in years. So when you try to find the growth rate, it'll be easier for Gwen's model because all you have to do is take away 1 from the b value, which is your growth/decay factor. When you do that, you get 0.036, and to get your rate, just multiply that by 100 to gain a percent. When you multiply by 100, you move it over twice. You end up with 3.6% increase. Remember, you want to state increase or decrease, so I'm going to write increase. Now again, the problem with Finn's model is that he decided to do it over a 10-year period, but we want it annual growth rate right here. So to make this a t and not a t over 10, what we're going to do is we are going to manipulate it. And we're going to manipulate it by taking the growth rate, 1.44, and separating the exponent to 1 over 10 times t. Now that is equivalent to t over 10 because it's multiplication. To get my annual growth rate, what I'm going to do is type this section into my calculator. So take a second right now, type that into your calculator, 1.44 to the 1/10. When you do that, you're going to get a value inside your parentheses that is more like a growth rate. When you get that value, you should end up getting something around 1.037. Now it's more clear to find the annual growth rate because you're not dividing the exponent by 10. Now your growth rate is into years and not 10 years. So I'm going to take away my 1 just like I did with the other one. I get 0.037. Multiply that by 100. His growth rate is 3.7% increase. And Gwen's growth rate is 3.6% increase. And actually they're very similar, which is a good sign because that means that both of their models are pretty valid. The next thing asks, what's the predicted population in the year 1790 for each model? Well, 1790 is the starting year. And if you look at the graph up here, that is where it starts, 1790. So if you remember in the formula, y equals ab to the x, so this being a and this being b, this being A, and this being B. If you want to find the population in the initial year, where 1790 is your initial year, you would just take the A values. So the initial population for Finn, he predicted 33,131 people, where Gwen predicted 48,661. I'm just going to go at the top to make sure that this is in the correct population number. Yep, so as in thousands. So this is the correct answer here. Now the bottom part says Lenny calculated an exponential regression using his graphing calculator and got the same growth rate as Gwen, but his initial population was very close to 0. Explain what Lenny might have used to find his function. Now, the only problem I can think that Lenny did was, if you remember back in the do now, I told you to use the initial year as year 0. Maybe Lenny used, maybe Lenny typed in the data using 1790 as year 0 instead of like changing all the values to 0, 10, 20, 30, and so on. The next question says, when does Gwen's function predict the population will reach 1 million? And how does that compare to the graph? So the first thing I'm going to do to solve this part is I'm going to take Gwen's function and I'm going to set it equal to 1 million people. So 1 million, 1, 2, 3, 1, 2, 3. Set that equal to 448,661, parentheses 1.036 to the t. So what I want you to do right now is find the t value that will make her population reach 1 million. So pause the video, try to solve for t. When everyone seems to be done, unpause the video. Okay, so the way you would solve this is you would first try to get your base and your exponent alone. So I'm going to divide by this. Hopefully you guys received an answer already, but I'm just going to show you how I would do it. I'm going to get a value about 20.55 and equal to 1.036t. Now I notice my exponent has my variable, so what I'm going to do is I'm going to log both sides so that I can get that exponent down. When I log both sides, what it does is allows me to bring the t down to the front. So now I have log of 20.55 equals t log of 1.036. T and log of 1.036 are connected by multiplication, so I'm going to divide. And when you divided this, hopefully you guys received an answer about t being 85.5 years. So that's not really answering the question though. That just gets you how long it's been since 1790, which is the initial year. So what I'm going to do is I'm going to add that to 1790, and that gets me a year of 1875. Now, what I want you to do right now is take a look at the graph on page 301. The graph on page 301 at 1875 looks like this at the top. So, if you look at 1875 around here, which is around there, probably that point, it's really close to 1,000,000. So, her function is pretty good. Her function is a really good prediction of the population in New York. The last question says, based on the graph, do you think an exponential growth function would be useful to predicting the population of New York in the years after 1950? Now, they're talking about after 1950. So when you look at this graph up here, after 1950, what seems to happen is that the population, after its rapid increase, starts to level off. And this right here, this section here, that leveling off section, looks a lot more like the graph of log, because it's starting to level off. If you remember, the graph of log looks like this. So after 1950, it might not be appropriate anymore for them to use a exponential function. It might be more appropriate to use a log function. So I would say a logarithmic graph would be more appropriate because the population starts to slow down and level off. The next section says, suppose each of the functions below represent the population of a different U.S. city since 1900. Complete the table below. Use the properties of exponents to rewrite the expressions as needed to help support your answers. First off, cross off function b. We're not going to do function b. So just put a cross through that. All right, so the first thing we're going to do is, why don't we fill in the column of each of these for the population in 1900. The population in 1900 is the initial year, and that should be easy for you to find because you're just going to look at the A value. So the initial population here is 3,000. Initial population here is 10,000, because there's a comma there, yep. And then the initial population here is 900. Now the last part says, find the annual growth or decay rate. I'm going to go backwards and go back to part A, well, function A last. Function D is easy to find the annual growth or decay rate because this is B, 1.02. And if you remember, the B is equal to 1 plus R when you increase. To get your R value, just subtract 1. So the R for this is 0.02, meaning that I have a 2% growth for this function. Now for the next one, it's decreasing. The reason why function C is decreasing is because you're subtracting from 1, meaning that you are going down and losing the population. So my function here is a 1 minus R situation, this being your R, and my R at this case is 1% decay. Okay. Now the last one's a little tricky because if you remember from one of the questions that we did I think part A with Finn and Gwen when you had to rewrite it. This function here is dividing time by 5. And that's not the annual growth rate. That's the growth rate over a 5-year period. And we want the annual growth rate. So what we're going to do is we're going to mess with this formula. And what we're going to do is we're going to take that growth rate or that power and write it as 1/5 times t. So 1/5 times t is the same thing as saying t over 5. So what I'm going to do is I'm going to plug this 1.1 to the 1/5 of my calculator. When I do that, you're going to get a value of about 1.019 to the t. Now you can identify r. R is that 0.019. Making a percentage moving over the decimal place twice, you have a 1.9% growth. And again, I'm growing here because my b value is bigger than 1. Okay, now the last section says find the population predicted in 2000. Well, 2000 is 100 years after 1900. So what I want you guys to do right now is just take A, C, and D, plug in 100 into T, and find the population in 2000. So pause the video, take a second to do that for me. Okay, so after you have typed all these 100 values in, for the first one, for function A of T, I received a population of 20,182. Again, with rounding, make sure you stay, or just don't round up with people. You don't want to make up half a person. With function C of T, I received an answer of 3,660 people, and with D of T, I received an answer of 6,520 people. Okay. The next thing says, between which years did the population double? Now, what you might want to do here is you might want to take out another piece of loose leaf because this might be useful. So I'll give you guys a second to do that. Or you can squeeze it on the side, that's fine. But all right, so I'm going to take my function 3,000, 1.1 t over 5 equals, I'm going to double this to be 6,000. Okay, so what I'm going to do is I'm going to solve for my t value. So if I divide by 3,000, I'm going to get 1.1 t over 5 equals 2. Then what I'm going to do is I'm going to take the log of both sides so I can bring down the t over 5. So t over 5 log of 1.1 equals log of 2. I'm going to divide by log of 1.1. Put that in parentheses. These cancel. And I'm also going to do something else in the same step. I know that I have t of 5 over 5 over here. And I know that if I multiply by 5 on either side, what happens is this cancels. So type that into your calculator, see what year you're going to end up getting. So when you type that into your calculator, you should end up getting, let me see what I got in my calculator. I got 35 point something or other, or 36.36 about. So this gave me a value of about 36.36. So what years is that happening in? Well, between the years of 1936 and 1937, because this is not an exact value. This is a rounded value, and it's happening between 1936 and 1937. It's kind of happening between a third of 1936. So my answer here would be 1936 and 1937. So let's now take a look at the next function, which is C of T. C of T, it's saying, when is the population going to double? Well, let's just be smart here. We have a decay rate. Is the population ever going to double? No, it's only going to decrease. So the answer to this is going to be never. Okay, so what I want you to do right now is pause the video and try to figure out when the population will double for D of T. So take a second, pause it, figure it out, solve for T. Okay, so what I'm going to do is I'm going to solve for T for D of T. I'm going to set it equal to 1800 because that's the double of 900. I'm going to divide by 900. I end up getting 2 because you're doubling. And then I'm going to take the log of both sides in order to bring down my exponent. And I get log of 2 equals t log of 1.02. And I'm going to divide by log of 1.02. When you do that, let's see what I got on my calculator. So log of 2 divided by log of 1.02, I got 35.002. So t is about 35.002. That means that it's happening again between 1935 and 1936 because they're happening at the beginning of 1935. So between what 2 years is it going to double? So a good estimate would be 1935 and 1936. Now the next question says, could the function 6,520 1.219 t to the t over 10, where t is the year since 2000, also represent a population of one of these cities, use the properties of exponents to support your answer. What I'm going to do is I'm going to change this function to an annual growth rate. And again, I'm going to do that by manipulating the exponent. So I'm going to make it 1 over 10 times t. I'm going to plug this into my calculator to find the annual growth rate. So when I plug that into my calculator, I end up getting 1.02 to the t. So let me just double check that. 1.2, 1.219 to the 1/10. Yeah, I got 1.02. Now, this is very similar to a function up here. It's very similar to d of t. If you notice, they both have the same b value. So d of t is very similar. So it says use the property of opponents to support your answer. It would represent d of t because they have the same growth rate of 2%. Which cities are growing in size and which cities are decreasing? Well, we know that a of t and d of t were growing because they had a b value that was bigger than 1. This one did not have a b value that was bigger than 1 because we were subtracting. So the answer to this, the ones that are growing are a of t and d of t, and the one that is decreasing was c of t. Which of these functions might realistically represent a population growth over an extended period of time? All 3 of the ones we dealt with are really realistic, A, C, and D. They all have a pretty good growth rate, nothing crazy, 2%, 1.9%. They're all good growth rates, so all 3 of them are very good. All right, guys, if you didn't understand this lesson, you can replay this tonight, and I hope that you have a great day.